Okay, so basically one person online, you can still communicate. Who's your teammate? Teammate of Infinity Who? Okay, so I think I'm going to turn the camera to your teammate. Okay, so you can talk to him, talk to her if you want to. Those two guys, your teammate, right?
Oh no,
No, wait, where? Where's your teammate?
My teammates are Dan and Matt.
I don't see them. Why? Okay, well, that's fine. That's fine. At least one member is here. That's good. Don't worry about it. So I hope they watch the video later. Okay, Dan and Matt. I hope you watch this video. Okay, anyways. Don't worry about it.
Oh my God.
So let's begin today with updates. Updates. What is update? Project phase 1B is due next Tuesday. And homework of Unit B2 is also next Tuesday. And then guess what? Thursday's exam. Okay, that's one. Sort of.
Wait, Dr. Hashibara?
Yes?
What's the likelihood of Unit B2 being on the exam?
Well, you have almost a week to do. I mean, you can't do it like a 3 problem.
What's the chance of a question from B2 being on the exam?
Well, I don't know. I haven't made up the exam yet, so it's up to my mood on the day of the exam. But you can handle, of course. It's an easy problem.
Hashibara, you're a great professor.
Really?
Yeah.
Wow.
You're an outstanding professor.
Is it the sarcastic or real?
No, I'm just being really nice.
Fail him for being
Yeah, so Unit B1, I'm not talking about B1 or B2. Sorry, okay. B2, yeah, okay. So Unit B2, how many problems do you have? 3, yeah, I mean, it's easy problems, right? I guess.
I can't copy them.
Don't say that. Even though it's true, don't say that. There's a solution.
Fail her too. Yeah, check the value.
This is aero anyway, so you see similar materials, yes, of course, from aerodynamics.
We're using our resources.
It's a resource, yes.
Resources.
Until he changes.
So after you go through aero 1, at least this section of this flight mechanics is a joke, right? You know everything. Kind of thing. It's all right.
We should.
Is it gonna get harder?
Huh?
Is it gonna get harder?
What is a hard problem? I mean, the only thing I can do is cut and paste. I mean, I don't wanna use my brain for exam.
So we can use copy paste too, right?
Well, if you do everything you should be doing, I guess exam is not exam, it's entertainment, right?
That's true.
Okay. Anyway, so you can do it. All right, so anyways, next Tuesday, everything you turn in, and Thursday you take the exam. Exam should be easy. Don't worry too much about it. I guess everything is aero. So it's almost like a review of aerodynamics. Okay. So you can handle that, except probably Jordan, because you have to study like hell. Yes. You can handle that.
Am I going to be all right for that? Because I spend like an ungodly amount of time.
Oh, yeah, I know that. And then, yeah, I think you can survive. No problem. Yeah. I don't do anything strange. In other words, what I'm going to do, my exam is, I guess you know that, I create the exam problem by basically cut and paste, changing a little bit, that's it. From your note, from the notes or example or homework or quiz or something, I start from one of those, pick it up and cut and paste and change whatever.
So I should
That's
focus
right.
on the homeworks and the quizzes then?
Yeah, homework and quiz is essentially forcing you to review aero materials anyways, but yeah, that could show up on exam, that's right. But nothing like all of a sudden shows up out of nowhere kind of problem. No, I'm not going to do that. Okay.
Question 4.
Question 4, yeah. Okay.
Your question 4 would be interesting.
Well, I mean, really? I mean, aero exam, there's no surprise, wasn't it? Yeah.
No.
There wasn't.
I don't want to do that, because that's a torture.
The only surprise I ever had was trying to turn it in, my printer chewing up part of my exam paper.
Oh, yeah, that's, yeah, too bad.
That was a nightmare.
Those kind of things happen, yes. But it's not my fault, you know. Yeah. Okay. Any question about the exam? Next Tuesday, you turn in everything. Thursday, you take exam. Right? That's what it goes. Okay. And then I'm going to put the solution always up before I start grading. So you have access to every solution. So I hope you know it. I mean, this is nothing new. I always post the solution. Okay. So you just always check against my solution for everything you did. Okay. So here's a solutions page. There's a meaning for it. Please use it. Okay. So today we are going to take a look at Unit B3, Advanced Subject, and an exercise. Okay. So what kind of advanced subject we're going to cover today? We're going to take a look at some supersonic airplanes, weird things, such as something called the pitch up. Pitch up is a very violent, very dangerous thing for supersonic airplane. All of a sudden, you lose the stability of longitudinal direction in high speed. It depends on the configuration. You really need to avoid it, type of thing. And also, leading edge type, depending on your wing shape, your high-speed airplane's leading edge needs to be carefully designed. Otherwise, you may potentially damage your airplane. Now, in this semester project, almost all the team heavily depend on X-Flyer 5. That means your design is probably low-speed airplane. Is that correct? I have no problem if one team try to challenge for high-speed airplane design using X-Flyer 5. That is okay, but you have to add certain amount of hand calculation for supersonic range. And then if you are designing your airplane for specifically only for low speed, I still force you to do high-speed calculation by hand, and then come up, the result will be potentially pretty bad. But it's okay because your design is only low speed. If you're designing high speed, I think you're going to add up your requirement that high-speed range of an airplane performs well. So that's the only difference if you choose to go with high speed. The difference will show up in phase 3. Okay. Now, phase 4 is stability analysis, static and the dynamics. So it's about the same thing. So if you choose to go for supersonic airplane, that's okay. Obviously, you need to carefully choose your shape and design of airplane to optimize at your supersonic speed, depending on the design. So it is going to change a little bit of the focus of what you are pursuing for. Anyways, let's take a look at the leading edge and high-speed pitch-up issue. Okay. So as you can see, two airplanes. One of them is actually, you have a real airplane sitting right next to the bookstore. This is a Starfighter. Now, obviously, the leading edge sweep is not so big. It's only this much sweep angle. So this airplane actually creates a shock wave starting from the root of the wing, and then the rest of the wing is outside of the shock wave. So obviously, this is called supersonic leading edge. You can't have much thickness. You have to have a razor edge, razor sharp edge, because your leading edge of your main wing is exposed to the supersonic flow. So you have to design and build based on that fact. Now, some of the airplanes, they have a specifically designed the platform that the leading edge sweep is inside of the shock angle. Shock wave is created at the root of the wing. That angle is called Mach angle. Your leading edge sweep is less than that. So entire wing leading edge, except the root, is inside of behind the shock wave. So that means you only experience subsonic flow behind the shock wave. So now the wing shape, especially leading edge, you can have actually certain thickness. In other words, you can have a rounded leading edge, and you can have fairly thick airfoil for that purpose. Okay. So this is the big difference between supersonic versus subsonic leading edge. So the design of leading edge comes in based on the choice of your wing platform. depending on your cruising Mach number, and the Mach number cruising condition is going to create certain angle of attached oblique shock waves. Okay. So if you go for supersonic design, you have to consider those things. Okay. If you just to design the airplane for your raw speed, you're certainly not going to design this kind of wing. You're not going to design this kind of wing. Those kind of design is horrible in low speed, so you're not going to choose those things. Okay. The other subject is something called pitch up. Okay. So pitch up is actually very dangerous. Okay. So this is happening for high performance airplane, typically high speed, with the swept surfaces and relatively low aspect ratio. What is that? Those two airplanes typically. And this is very low aspect ratio wing. This is a highly swept delta wing. So those kind of shape is chosen because you want to optimize for high speed performance. However, this actually sometimes causes pitch up. Okay. This is the undesirable nose-up pitching moment at high angle of attack. Let's take a look at the plot here. So this is something called pitch up. So this is a plot of CMCG. This is a center of gravity moment coefficient. In other words, how much moment is going to be developed at the center of gravity. So naturally speaking, as you fly your airplane in high speed and high angle of attack, how much moment you are going to experience. Typically, this is the normal behavior. In other words, if you're trying to pitch up your airplane, the airplane's natural tendency is trying to pitch down. In other words, negative value. And if you pitch up more, that tendency becomes higher. So if you try to pitch up more, airplane try to resist to go back to the horizontal attitude. So this is a normal response, but some of the airplane actually responds like this. You know, this is very dangerous, isn't it? This is called pitch up. In other words, if you try to pitch up, airplane pitch up more, easily diversify your maneuver, it is going to be a very dangerous situation. And then it is not easy to counteract and go back to normal situation. This is called high-speed pitch up. It's not very good. So you have to avoid it. And then oftentimes, this is observed for V-tail design. This is very well known. So if you choose to go for V-tail, V-tail airplane have this tendency. So you have to avoid it. And also, aspect ratio and then sweep is going to come into play. In other words, if you plot aspect ratio against leading edge sweep angle, this is a plot, and then if you go across this boundary to the right, you have most likely having the tendency of pitch up for your airplane. So you should probably keep your design inside of this boundary. So this is going to actually limit very radical design, such as, okay, so I'm going to design leading edge sweep angle 20, however, very good high aspect ratio. What kind of airplane? It's like a very slender, high aspect ratio, not so sweep. It's like a glider. Well, it's not good for high speed anyway. And then it's like, whoa, I got 80-degree sweep. Like, what kind of a wing is that? Like this kind of wing. And the aspect ratio is kind of high. What do you mean? It's like a, I don't know. It's like a radical B-52, highly swept B-52. That's not good either.
Oh, no.
That's terrible in those speed, probably. I guess so, yeah. So those are the boundary to avoid the pitch up. Okay, for supersonic airplane.
Versus about 20-degree sweep.
Yeah.
It's about 20-degree sweep, then aspect ratio of 9.6.
20 and 9.6. Oops.
I'm at the edge of the curve. Whoops.
Oops here.
Oops.
So that airplane may potentially
decrease
kill
that sweep
someone. Suppose if you design an airplane and somebody die, okay, your life is over. As an airspace.
Time to decrease that aspect ratio.
So you probably either decrease the aspect ratio or
Decrease the sweep.
decrease. Yeah, but if you don't want to decrease the leading edge sweep.
No.
Yeah, okay. So those are the design choices you have to face. Okay. So next page, I'm going to spend some time today talking about stealth technology. Now, I have to tell you that I'm not the specialist of this technology, and then information is not really available in public domain at all. So those information is just basically coming from Air Force Academy's textbook. So this is as much as I can share as a common knowledge for stealth technology. And then also, this winter break, I took my son to Ohio and also Louisiana. The reason is Ohio, my son wanted to go to U.S. Air Force Museum, and then Louisiana, he wanted to go to World War II Museum. Yeah, so his favorite is kind of sort of biased on certain area, either battle, war, World War II, or airplane. And he's a biology major freshman right now. I don't know what's going on.
Did you allow that?
We have biology major, yes. So students can be a biology major at Embry-Riddle. There's not many people like that, but
Well, why is that engineer?
I don't know. He resists to be an engineer. I don't want to take your class, maybe. I don't know. Could be. But he enjoys biology. I mean, he's just coasting every day. Unlike you, too bad. Well, he comes into the lab, right? Do you talk to him? No, he says, oh, she always ignores me. She's always tense and ignores me. Because, well, of course, she's under lots of things. She's working, she's doing research, she's taking daddy's class. That's enough, kind of thing. I don't know. But it's okay. Just ignore him. Continue ignoring him. Okay. So this is a 5th generation fighter. So obviously this is B2. This is F-22, right?
That's the YF-22.
Yeah, it's live.
YF-22.
Yeah.
Oh, this is YF-22. That's right.
It will eventually become the F-22.
Ah, okay. So those two are different. That's right.
Yeah.
Okay. I don't know what this thing is.
Oh.
That's just
I just made up something, right?
Yeah.
Okay.
I'm maybe with that.
Yeah, I have no idea. So first of all, they talk about aspect angle. Aspect angle is, interestingly, if you're standing here and then look at the horizon and then you see airplane coming in, what's the angle? That's aspect angle. It's like a rough estimate of, okay, so this is the angle from your ground point of view to the airplane. How much angle do you have? It is sort of like a combination of distance and elevation at the same time. So how far you can see your airplane, okay, that's the aspect angle kind of thing. Okay, so this is like a ground radar point of view type of thing. So they concentrate on two areas. One is a radar signature, and also sensor signature too. So let's just cover those things. First of all, leading edge sweep. You have to have a sweep angle. In other words, if you don't have a leading edge sweep, radar wave comes in, hits right back. It's not good. So you want to have somehow radar wave incoming deflect to the different direction. So sweep always comes into play. Low speed, high speed, it doesn't matter. F-117 is a low speed airplane, but still has a sweep. Okay, so they actually sacrifice low speed performance for stealth. And planform alignment is kind of interesting. They always want to align the angle of leading edge and trailing edge. Wait a minute, not this one, not this one. This one, here we go. So this is a planform alignment. So you want to align leading edge to those angle as much parallel as possible. Okay. In other words, radar wave gets in and leaves in a different direction. In other words, it is going to concentrate on certain angle only. So you're going to have a radar spike at a certain angle, but no other angles. Rather than having high diffraction all over the place, it's called the fuzzball of the radar. You're going to actually reflect into certain direction only. So as long as the radar is looking at you with that angle, radar signature is minimized. That's the idea. Okay. So that's called planform alignment. And at the same time, leading edge and trailing edge both need to have a sweep angle, and oftentimes those angles are parallel. which is the same angle. Okay. All right, here we go. And also, fuselage should have angle too. In other words, radar incoming hit the fuselage. You're going to have an angle so that the radar signature goes toward a different direction. Okay. That's called the fuselage aligned. What's that? I don't see it. Well, anyways. And also fuselage shielding, you're going to have a special coating paints for the fuselage. Vertical tail is also lined up with planform angles. Okay. And then this is the sharp corner or chin between the sloped upper and lower sides of the low radar cross-section fuselage. That's what you're seeing here. So this is called chin. Okay. Next one is what? Radar absorbing materials. I don't know what type of material exactly, but every stealth airplane comes with radar absorbing materials and also infrared absorbing materials. So this is actually true if you try to make a very good snapshot using like autofocus camera. Sometimes it cannot focus because it's just being absorbed. So oftentimes you see a difficulty of taking a good shot of the stealth airplanes. I'm going to show you some pictures later for you. One of them is actually not focused at all, and I kind of suspect, oh, this is absorbing. I don't know yet, but you know, I can show you the picture. Scuffed indents. Obviously, the indent, some of the airplanes, conventional type, have an indent which is completely perpendicular to the flight path, which is not good. Your stealth airplane shouldn't have a completely perpendicular surface against the flight. In other words, if the radar gets in, it hits right back. So you want to have all the angle, okay? So indent rib edges perpendicular to the aircraft flight path is not good, so they want to avoid it. So this is like a diamond shape, sometimes called scuffed indent. And also, human eye is a sensor, of course. So the choice of the color is also quite important. So U.S. Air Force actually now employs medium to dark gray, with no sharp changes in color usually produce the lowest visual signatures, so against human eye. So they carefully choose the colors too. Okay. Next page. So this is the radar signature response comparison between stealth type and non-stealth type. This is called fuzzball of radar signature. So if you don't have a stealth type of design, you have all over the place fairly high radar signature. Now stealth means you're going to concentrate on certain direction. So if the radar is looking at you from 90 degrees from the side, of course you're going to see it, but that's the only angle you're going to have a strong response. So design-wise, you're going to reflect back into the certain direction so that you're going to overall minimize your radar response signature. Okay? And this is F-117. You have indent, which is not exposed at all. This is an indent screen. And then engine indent have a curved path so that the radar signature is not going to reflect back to you. You're going to have a serpentine type of shape of a engine indent. So radar signature doesn't respond back to the source. And also you have a screen, and also sometimes exhaust location is kind of interesting because the engine exhaust is not really exposed to the ground. Engine exhaust is on the top here, covered up by the fuselage here. So I took some interesting pictures, you know, in Ohio, so I'm going to show it to you. So those are the kind of things people know that as a common sense nowadays. Lots of more details, but it's not available in common, in public domain. So I have a few photos here. Okay, so this is the B-2 bomber. I took it, close-up photos. It's actually surprisingly very close. You can actually touch the airplane, you know. It's quite interesting. And then one thing I noticed was, you know, look at the surface wow, this is so smooth. It's amazingly smooth surface here. So you can even actually go down the fuselage and take a picture here, and then I realized afterwards this is not focused at all. It's all fuzzy. I mean, it's kind of hard to see for you, but this fuselage is like out of focus all the way through here. So you just keep focusing on other things and not trying to focus on the fuselage all the time. And the fuselage has a very plain flat surface, very super smooth. It's very difficult to autofocus anyways. Okay. And this is the interesting angle snapshot from one end of the wingtip. It's a very straight line with a sweep angle. And the sweep angle is lined up with a trailing edge. Okay. And then this is a frontal picture here. I guess you can see the cockpit and also engine inlet. So engine is mounted sort of like on top of the main wing. It's more or less like a Honda Jet kind of design, right? There's a student actually graduated 3 years ago, got a job at the Honda Jet. This is YF-22. This is F-22 Raptor. This is, I think, the prototype 1 or 2. I don't know either way. You can see, obviously, this is a scuffed inlet, and also this is a cutout for the boundary layer. And you have a weapon bay integrated also in the cowling, and then cockpit shielded. Okay, so this is more like a crossing view here. This is the engine, which is completely separated from the fuselage, main body, and then mounted right next to it, placed in next to it. So this is actually, you're looking at engine exhaust outlet with the thrust reverser plus vector control of the engine nozzle. Okay, this is a little bit more closely picture. Pratt & Whitney L100. Okay. So this is the other side of the picture here. By the way, my son is watching. Okay, so he's actually reading the description of this airplane. So this is integrated weapon bay. Basically, you open the door and then launch the missile. Everything is stored inside, obviously. This is YF-23. Yeah, I think this is the one lost in competition, right?
Mm-hmm. Yep.
Okay. And then this one is on display. I was able to approach the backside of the airplane. That's kind of interesting. So I took the snapshot of this airplane too. This is the engine inlet below the main wing, and then engine exhaust is above the main wing. It's interesting. It's a serpentine design. Now this is the engine exhaust, which is shielded from the ground, so no one can actually see the engine exhaust from bottom, because it's mounted on top of the fuselage. It's completely covered up from the ground. Okay, so this is like a view out. I guess that's it. So this is the some selected pictures of Ohio Dayton U.S. Air Force Museum. By the way, this is completely free. They have like 5 huge hangars. You can walk around, touch the airplane. You can take the snapshot. You can even on board of the airplane. Sometimes a special event at night, some retired U.S. Air Force people come in and then show the airplane. Hey, this is the airplane I flew in World War II. This is the details. You can touch the control. Well, you can get into the cockpit. I mean, that's amazing. We went there 9 a.m. I left like 10 p.m. Yeah, and then my son said, well, I need to go back tomorrow too, kind of thing, because it's completely free. They don't charge anything. Okay, it's a free exhibit. A huge collection of Air Force airplanes. Insane. And then there are lots of communication you can do. You know, people sitting there, they want to chat with you, especially if you see, hey, where are you coming from? Wow, I'm from Embry-Riddle. Oh my goodness, you have a seat Sit down. Do you want a coffee? And then ended up having 1 hour chat with retired World War II Air Force officer. Oh my goodness. Okay, anyway.
You can get a flight from Phoenix to Dayton through Chicago for only $200
Yeah.
on Southwest.
Oh yeah. It's worth the money, yes.
Yeah, field trip.
Field trip.
Field trip?
Get the school to fund it.
Yes.
As a matter of fact, I kind of start thinking about it. That's a good idea.
Yes.
And then they actually have an exhibit of NASA, also space shuttle and then rockets. There's a cafe in the middle of the hangar so that people actually watch the airplanes and rockets and spacecraft and eating lunch. Oh my goodness, that's how beautiful it is kind of eating lunch. So yeah, that facility is amazing. Okay. Yeah, okay, so thank you for that. I'll think about it, okay. All right. So let's just go back for a moment to the lecture. I don't want to lose the focus here, so let's just go back here. So one more thing I want to cover here is you have to actually integrate your propulsion system with your body. And then remember area rule based on the Sears Huck body. This is the cross-section area plot over the line of fuselage from nose to tail. You have to have a certain distribution of the area ratio in order to minimize the wave drag. Do you remember that? So some of the airplane has a cork bottle or wasp waist shape in order to minimize the wave drag. Now, almost all the time, the actual airplane do not follow that rule, okay? The reason here is they want to integrate your propulsion system, and you don't want to have the inlet of the engine behind the stronger shock wave. In other words, once your body creates the shock wave, everything behind that shock wave is going to be subsonic, and then you lose the total pressure, you lose the total density, everything is kind of reduced. So it is good to minimize the drag, but it's not good for the engine inlet, especially engine inlet. You want to retain the higher pressure, okay? So oftentimes, you're going to change the shape into this way. You're going to purposefully allowing the shape to create the series of weaker shock wave before you hit the inlet. In that way, it is better for engine. Obviously, you're going to increase your wave drag for your airplane, but it is better for your engine. So oftentimes people do that. They deviate from this. This is the ideal plot based on the CS Huck body function, which is area ratio need to be distributed like this. If you strictly follow that rule, your fuselage needs to be wasp waist, but oftentimes, if you're trying to integrate your propulsion system in high speed, it's not the best choice. Okay, so this is the location of inlet, and then this is the actual distribution of the area ratio of each airplane. Okay. Yeah, so that's the engine airframe integration. So now, starting from page 7 of this unit B3, okay, this is entirely an example of hand calculation to predict your overall airplane lift coefficient and also airplane drag coefficient, entire airplane. So this is the hand calculation example. You need to do the same thing at phase, what phase? Phase 2 of your project, okay? So this is theory-based hand calculation. This is the whole airplane lift and drag. Okay. I think we talked about phase 2 already, maybe not. So let's just take a look at phase 2 of the project for a moment. Okay. So phase 2 of the project, obviously you're going to complete 1B next week, and after that, what happens is phase 2. So at phase 2, based on the phase 1 and phase 1B, your team is going to come up with the baseline requirements of your design. What kind of airplane you're going to design, what is the constraints, what is the performance you want to achieve, kind of thing. And then based off of it, each member is going to design the cross-section, and based off the cross-section, you're going to actually design the wing, and each member come up with your own idea of the best design of the wing. And then as a team, you come together, hey, let's pick up this wing design. Based off of that best wing design, once again, each team member come up with the airplane configuration. Okay? Then you're going to come together and compare, okay, which one actually came up with the best overall whole airplane configuration. Okay? So at this point, phase 2, your design is sort of quickly come to pieces. Okay, so this is our airplane looks like. It's the best choice out of all of those members' contributions. Now, based off of it, obviously X-Flyer 5 is going to, of course, compute the whole airplane lift and drag coefficient very easily, because that's what the software does. Now, I guess the heavy requirement at this phase is, obviously, you have to compare that result against the hand calculation, okay? And then you have to compare that. So hand calculation, no one likes it, of course, but I have to force you to do it. Otherwise, Dr. Jeff Ashworth may say something to me. You're a computer geek, not the airplane designer. He usually say that. I made my students' hand calculation. Okay, I'm happy now. And obviously, this is important because as you try to do hand calculation, you really need to know literally where does that coming from. Some of the information come from theory, some of the information actually come from empirical information, past experiences, accumulated data, lots of varieties. But you have to understand why this number should be chosen to have a fairly accurate estimate. So this is the example for F-16 airplane. So this is the configuration given for F-16. And then you should have the same configuration given from your X-Flyer 5. Okay? And then at this moment, you have a sizing not completed, but you come up with certain sized tail, stabilizing surfaces, and also control surfaces. For upsizing, you need to kind of probably resize it later, but you can come up with certain size and configurations. And then you're going to go through this example to compute span efficiency factors, compute lift curve slope for main wing and tail, and then lift curve slope for added surfaces. And then you're going to compute, this is the rate of change of the downwash angle with respect to the angle of attack. You're going to compute it. And then takeoff and landing configuration, you need to come up with it. X-Flyer 5, of course, allows you to put high lift devices on it. So based on your current configuration, you're going to come up with augmented lift coefficient for touchdown and takeoff. Okay. So this is F-16's takeoff and then landing approach configurations given. And also this is the surface which is simplified for F-16. In other words, back in old days, there's no CAD, everything is hand-drawn drafters. It is fairly difficult to come up with the surface area of the entire airplane. You have to simplify series of simple shape. In this case, this is a simplification method. So this is the F-16, which is simplified with a series of simple shape. In other words, triangular shape. This is cylinder. This is a tapered cylinder. This is another triangle. Those are the area which is estimated, what's estimated, or like a simplified surface. You're going to add them up. Next page, yeah. So this is a weighted area estimation. You're going to use the series of simplify the surface shape and then add them up to come up with weighted surface area. Nowadays, because you're using CAD is capable to give you a weighted surface area, but that's it kind of thing. But back in old days, this is the only way to determine weighted surface area because everything's drafted on a piece of paper. Okay. X prior 5 may and may not, I don't know, you have to find out, may and may not give you the weighted surface area as a data. I think they will. I hope. If so, it's easy. You can replace that weighted surface area estimated and compare it against, if you simplify all of those areas using those simplified shape, compare it against, so what is the estimated weighted area versus X prior 5's actual weighted area kind of thing? Because weighted area is going to impact on your parasite drag coefficient, right? Okay. Zero lift or parasite lift coefficient, parasite drag coefficient, I should say. Weighted area comes into drag. That is going to give you total drag coefficient due to skin friction drag. Okay. All right, then you're going to estimate the total lift for a given angle of attack or a given configuration of takeoff and landing. Okay. So that's going to be probably a single or 2 or 3 data points. X5 actually give you multiple data points so that you can plot it. So you can easily compare how the software generated value against the hand calculation value. Okay. So this is a verification process of your software code. And then once the software is verified, you're going to put the trust on the software and then move forward, doing a series of different configuration, and then you're going to simulate. So simulation-based design optimization you can do. Okay. So this is a demo for that. So you are going to go through the step-by-step process for lift and drag. So a drag, of course, you're going to estimate parasite drag and induced drag. Those two added together for low speed. And if you go for high speed, of course, you're going to add supersonic drag, wave drag, and then you're going to estimate and add it to. Even though your airplane is designed only for low speed, you're going to compute this one. Of course, X prior 5 cannot do this, okay? Let's just note. Supersonic drag, this is hand calculation only. X prior 5 is not capable. Okay? So if your airplane is designed only for low speed, you're going to go ahead and do this to find out if this airplane flies high speed, what kind of drag increase am I going to expect? It could be fairly bad value, but you can find out anyways, okay? So this is entirely example so that you can use to finish up your project phase 2, okay? All right, so having said that, I have a few more things to share today. So this is basically Unit B3 done. So I can possibly say Unit B3 homework is due, blah, 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 but let's do it after the exam, okay? All right, so exam material covers up to Unit B3. I can safely say that. I'm not going to probably cover Unit C. Unit C is a performance, so it's not aerodynamics anymore. So let's just assume that the first exam will include only Unit A and the B materials, okay? All right. So I have a few more collection of photos here since I took my son to Louisiana. This is New Orleans. This is the National World War II Museum. It's a really highly renowned museum. He really wanted to go. And then, again, we spent 2 days just watching World War II all the way through. Okay, anyway. And then also Louisiana, this is Baton Rouge, right by the Mississippi River. There's a USS Kidd. This is destroyer, World War II destroyer, which is restored here. And you can kind of freely get inside, take a look at everything. Yeah, this is the USS Kidd. There's a building right next to it, the USS Kidd Museum. Okay, so this is a fairly small ship. Typical World War II U.S. destroyer ship. This is the torpedo tube. Here's the. Oh, okay. So I kind of find an interesting thing here. Okay, let's just zoom in. There is a teenage girl volunteered to work something, painting the ship or something. So I stopped at saying, what are you doing? Oh, yeah, I'm volunteering. My grandpa went to World War II and with this ship, and then he came back, survived, but his best friend died in Okinawa in 1945. This is, I think, 38 people died right here on this spot. There is a kamikaze attack happened right here on this spot, so 38 people died. And then, oh, okay, so by the way, we are from Japan.
Oh, no.
Yeah, I said it, yeah.
Wow.
By the way, I'm from Japan originally. My son is born here. I'm a U.S. citizen, blah, blah, blah. Well, she's very nice. Oh, okay. It's the wrong way you come from. And then, back in 1945, we are at war. Yeah, it's amazing now. We can see those things. So we had some discussion, communication. And then I don't want to emphasize my origin as a Japanese because it has probably not much difference been against other people, but since I have a unique background being a Japanese, I was born and raised in Japan, of course, way after World War II, I have nothing to do with those incidents. But because I was born and raised in Japan, I do understand the culture, history, and all of those things, much more detailed, those things, than, I should say, quote unquote, Americans. I'm American, I'm a US citizen, but I'm naturalized citizen. Okay, so yeah, this was a very interesting encounter. My son was, again, born and raised here, so he considered himself, I'm American, I'm not Japanese. Well, okay, biologically speaking, you're 100% Japanese because your parents are 100% Japanese, they're immigrants. Well, I'm US citizen, I'm American. So that's the mindset, which is great. Highly valued, mindset as being American. So let's go back to Ohio once again. Air Force Museum. I found this airplane. Okay.
That's an interesting
Oh.
one.
If you know what it is, I guess you know what it is.
Oh.
Yeah.
Oh, yeah.
Oh, yeah?
Yeah.
Okay, so.
Looking at the markings again.
Okay,
like,
so
oh,
if
yeah.
you know what this thing is and the mindset under the World War II, if you were aeronautical engineer during the World War II, you may end up designing this kind of thing. How do you feel? I mean, you can never experience such a thing unless you were there. So since I'm Japanese, I can sort of tell, and then I chose to be aeronautical engineer coming to United States. I have a few thoughts sometimes, when you do something, trying to achieve something, motivation, purpose, goal is everything. Sometimes. If you begin something with the wrong motivation, you may end up having this kind of thing. It's not necessarily good or bad. This actually happened. Okay, I don't have any opinion. I have rather a negative opinion. If I'm forced to design this kind of thing, I would probably say no. How many people actually know what this thing is? 3 people, 4 people. So half of the class have no clue what this thing is. This is it says MXY7-K1 trainer. So this is a trainer airplane. So you use this airplane to train up pilots. Okay. What kind of pilot is that? I have okay. So if you go back to the home page once again, I actually post a video. Yeah, this is instructions media, parentheses optional. This is a optional video, okay? There's an audio, but it's completely Japanese language. It's subtitled. So you don't need audio. Let's just take a look at it. You don't need audio. because it's Japanese. It's just a putback audio.
現在、ゲットラインに接近。潮を
Yeah, it's Japanese.
了解している。高度4000に敵意16。
That's American. Well, this is Japanese anime. Why, yes. Okay, so this is a very classic anime, kind of old, and it's posted here. So if you're interested, just go ahead watch it. That's fine. It's a Japanese language English subtitle. Okay, so let's go back to the picture here. So what is this airplane? This is a flying bomb pilot trainer. You train the pilot, then pilot will die, 100%. It's a human bomb pilot trainer. I mean, are you going to design this airplane if you're under the same situation? I kind of come to think about it because I'm Japanese. If I'm under the World War II and then I'm forced to design this, I'm an aeronautics engineer. Am I going to do that? I don't know. It's like a really facing the serious question about lots of things, since you are trained up with a certain skill sets, and then it could be abused, could be used up in the right way, and then you have to make a decision. I know the true story who actually designed and built this airplane. He is a U.S. Imperial Army engineer. I think he's a lieutenant colonel. And then he designed and built about 1,000 airplane, and then he watched every day. Main pilots of this human bomb is about 18, 19 teenage kids. It's toward the end of the World War II. He saw every day like a 10, 20, 30, 19, 18 years old kids fly this airplane, never come back. Okay. He had very difficult time after the war. So he decided to quit being an aeronautics engineer, but the government picked him up and he's assigned to design something different. It was a bullet train, high-speed train system that Japan has right now. So I think he, as an engineer, he didn't want to see people die based on my designed vehicle. So that bullet train, actually, after they designed and invented after 40 years, now it's like 75 years now, nobody died on any accident on that bullet train. So I think, it came to think about lots of things. Traveling with my son, talking about, engineering is a serious business, people's lives on you. And he said, well, I'm not going to be an engineer, don't worry about it. Okay. All right, that's fine. So anyways, that's a little bit of side story, okay, from Ohio, okay? So let's just stop here today. Well, wait a minute, it's not still one. You still have time, but I'm reducing you already, okay? So we are done Unit B3 today. Okay, so have a wonderful weekend. We're gonna see you back on Tuesday. Next week is exam week, okay? Study hard.
And
Okay.
so I come back to my designer with some of the core lengths.
Have a wonderful weekend. See you guys next Tuesday.
Where you wanna go?
I'm pretty free for the rest of the day until like after 4.